Hello everyone. Hope you are doing very well. So, as you all know that today we are going to cover the theory part 3 of our chapter coordination compounds. So, let's begin our today's topic, that is NCERT chapter 5 coordination compounds theory part 3, and today we are going to cover the NCERT section 5.4 to 5.4.4. This is disclaimer. So let's begin with the objective. So after attending this lecture, you will be able to define different types of isomerism in the coordination compounds. So today our main focus will be the isomerism in the coordination compounds. The topics that we are going to cover today according to the NCERT are: the first is the section 5.4, isomerism in coordination compounds. Then the section 5.4.1, geometrical isomerism. Then the subsection 5.4.2, optical isomerism. Then our subsection 5.4.3, linkage isomerism. Then 5.4.4, that is coordination isomerism. And in the end, we will solve some example from 5.4 to 5.6. Let's begin with our first section, that is 5.4, isomerism in the coordination compounds. So let's talk about the isomers. Isomers are two or more compounds that have same chemical formula but a different arrangement of atoms. Okay, so isomerism comes when we have two or more than two compounds present having similar chemical formula. That means the molecular formula is same for those two compounds, but their characteristic or their arrangement, you can say their arrangement in the 3D space, are different. So isomers differ in one or more physical or chemical property due to this different in the arrangement of atoms. Okay, whether they are having the same chemical formula, still they are having different arrangement of atoms. That's why we are calling them as isomers, and due to this they differ in one or more physical or chemical properties. The two principal types of isomerism are known, which can be further subdivided. So we know our two major or two principal type of isomerism, under which we can further subdivide the isomerism. The first is stereoisomers. And stereoisomerism, the first principal isomer. In this, we cover the first type of isomerism as geometrical isomerism, then optical isomerism, and second principal type of isomerism is structural isomerism, in which we can subdivide it in the linkage isomerism, the coordination isomerism, the ionization isomerism, and lastly the solvate isomerism. So under the two major principal type of isomerism, we have in the stereoisomerism we have two subdivided isomerism, geometrical and optical, and in the structural isomerism we have linkage, coordination, ionization, and solvate isomerism. So today we are going to cover these four types of isomerism: geometrical, optical, linkage, and coordination. Let's begin with the geometrical isomerism first, which comes under the stereoisomerism, right? So our subsection 5.4.1. This occurs in the complexes with different ligands when they can be arranged in multiple spatial ways. So when the geometrical isomerism arises, it arises in the complex which is having different ligands. Okay, you can say homoleptic complex. Okay, heteroleptic complex, not homoleptic, where the ligands are different. Okay, so where the ligands are different and they can be arranged in multiple spatial ways, then this geometrical isomerism arises in those complexes. Examples of this behavior are found with the coordination numbers 4 and 6. So the complexes which is having the coordination number 4 and coordination number 6, in those complexes we show or we see this geometrical isomerism present. In a square planar complex, if you talk about the square planar geometry complex of type MX2L2, where X and L are different ligands and they are unidentate, that means only one donor atom is present in the X and L ligand. Okay, one more thing, coordination number we are talking about here, that generally this behavior, that means this geometrical isomerism, is found in the compounds having coordination number 4 and 6. Coordination number is referring to the number of the bonding atoms in the present in the ligands, or you can say the number of ligands that are present around the central metal in a complex, that is considered as coordination number. So if the ligand are 4 or 6, generally in those complexes we can see the geometrical isomerism. Now here in a square planar complex we have taken of type MX2L2, where M is the metal, central metal, X and L are different ligands and they are unidentate, that means only one donor atom is present in each ligand. Two ligands of X, when arranged adjacent to each other, they will form cis isomer. Okay, so in this square planar complex of MX2L2 type, if you arrange the two ligands of X in a adjacent manner, like one X is adjacent to another X in the geometry or in the square planar geometry of the complex, then that structure is having cis isomer, or that structure is the cis isomer of this complex. And on the other hand, when they are arranged opposite to each other, like the two ligands X, when you arrange opposite to each other, that means like their bond angle will be 180 degree between them, right? So when you arrange the two ligands opposite to each other in a square planar geometry, then the trans isomer will be shown by the complex. Okay, this is depicted in the figure 5.2. So let's see, this is the figure 5.2 showing the geometrical isomers in the cis and trans form of this complex platinum NH3 whole twice Cl2. Okay, here we have this platinum. So platinum is combining with two molecules of amine and two molecules of chlorine, right? So when let's say this is okay, so this is already of type MX2L2, right, where M is platinum, X is you can take chlorine, L is you can take amine, right? So when you are arranging X to adjacent to each other, so when you are arranging the chlorine adjacent to each other, then this structure is forming the cis isomer, right? Now when you are arranging the X opposite to each other, like one chlorine is here and opposite to it other chlorine is here in the geometry, right? Similarly, the amine are also opposite to one another, right? In this structure we can observe the trans isomerism under the geometrical isomers. Okay, so these are the geometrical isomers, cis and the trans form of this particular complex as shown in this figure 5.2. Square planar complex of the type MABXL, where the A, B, X and L are unidentates. Again, the only one donor atom is present in these ligands. So if you have a square planar complex where metal is there and four different types of ligands are present which are unidentate, they show 3 isomers in total, in which 2 are in the cis form and 1 is the trans form. Such isomerism is not possible for a tetrahedral geometry. So here it is a point to note that geometrical isomerism is not possible for a tetrahedral geometry. Okay, you know the tetrahedral geometry, that means the central metal will attach with 4 ligands or 4 side groups, okay, which can arrange in a particular tetrahedral geometry. So if our complex is in the tetrahedral geometry, it can't show, or it will not show the geometrical isomerism. Same is possible with the octahedral complexes of the formula MX2L4. So if we have octahedral complexes, octahedral means the central metal is connected with 6 different number of different ligands. Okay, so the formula is for that ligand is for that complex is mx2l4. So L ligand, X ligand, X is 2 and L is 4, so total is 6 number of ligands that are connected with the metal. So geometrical isomerism you can see in the octahedral complexes. Now the two ligands that are that is X may be oriented either cis or trans to each other. Okay, so the two ligands present in this octahedral complex mx2l4, these two ligands may be oriented either in the cis or the trans form to each other. How? If you place them adjacent to each other, then cis form will be there. If you place opposite to each other, the X, then the trans form of the isomerism will be there, right? So let's see this in the figure 5.3. This is the figure 5.3 showing the geometrical isomers, that is cis and trans form of this complex cobalt NH3 whole 4 Cl2 whole positive. Okay, where cobalt is, and this is a octahedral complex where central metal is cobalt connected with 4 different molecules of amine and 2 molecules of chlorine. Now let's say these 2 molecules are X molecule, which are 2 in number, right? So X ligand, that is chlorine ligand, if placed adjacent to each other, then you obtain a cis form. And if they are if the chlorine or X ligand is placed opposite to each other in the complex, then they are called as trans form of this isomerism, right? So these are the geometrical isomers in the cis and the trans form, and how we can obtain them in the octahedral cases that you have already seen of, and this is of the type mx2l4. This type of isomerism also arises when the diadentate ligands like LL. Okay, LL means the two ligands present in a single molecule to become a one ligand. Okay, and it is acting as a diadentate ligand. That means 2 donor atom is going to be present in that ligand. Okay, so this type of isomerism, that is geometrical isomerism, also have you can see when the diadentate ligand of type LL, for example NH2 CH2 CH2 NH2, that is ethylene diamine, where this nitrogen terminal nitrogens will going to act as the donor atoms. So when the complex is having diadentate ligand, okay, of formula mx2ll whole twice, then this can also show geometrical isomerism. Okay, so if you have a complex of type mx2ll2 where LL is a diadentate ligand, that means 2 donor atom is present in the same ligand. For example, En, that is ethylene diamine, NH2 CH2 CH2 NH2, then this can also arise the geometrical isomerism. We can see this in the figure 4.4, 5.4, where the geometrical isomers in the cis and trans form for the cobalt Cl2 En whole twice is given, where chlorine is a unidentate ligand, meanwhile En is a diadentate ligand. Okay, and how we can arrange that? So cobalt is a central metal, so it is present here in the center. 2 chlorine are placed adjacent to each other, and 2 En molecules of diadentate ligand is placed adjacent to each other, forming the cis form. Similarly, when the 2 chlorine are placed opposite to each other, and in the similar way the 2 En diadentate ligand molecules are placed opposite to each other, then you are obtaining the trans form. Okay, so in this type of complex mx2ll2, where LL is a diadentate ligand, this can also show the geometrical isomerism in the cis and trans form. Another type of geometrical isomerism occurs in the octahedral coordination entities of the type Ma3B3, like cobalt NH3 whole thrice, NO2 whole thrice. So there is another type of geometrical isomerism that you can observe in the octahedral coordination entities. Okay, octahedral coordination entities means, again, the central metal is going to attach with 6 different molecules of ligands, and it is of type Ma3B3. For example, cobalt NH3, the ammonia molecule in the 3, and NO2 molecule in the 3 amount, in the 3 number. It is representing the complex of type Ma3B3, a octahedral coordination entity, which show a different type of geometrical isomerism. And what is that? So if 3 donor atoms of same ligand occupy adjacent position at the corners of an octahedral face, we have the facial or FAC isomer. Okay, this type of isomer comes under the geometrical isomerism, shown by the octahedral coordination entity or octahedral complex, okay, of type Ma3B3. Now, 3 donor atoms of same ligand, what does it mean? So if you take this example of cobalt ammonia whole thrice, NO2 whole thrice, 3 donor atoms in the ammonia molecule, that means in the 3 molecules of ammonia ligand, we have 3 nitrogen, right, that are going to be our 3 donor atoms of same ligand ammonia. So 3 donor atoms, that is 3 nitrogen molecule in the 3 ammonia molecule of same ligand, that is of same ammonia ligand, occupy adjacent position. When it occupy the adjacent position at corners of an octahedral face. In the 3D geometry, when the corners of the octahedral face is occupied by the same 3 donor atom of same ligand, we get facial isomer. Okay, we will like understand it through image. Let's see the second type of geometrical isomerism, because if one is there, facial isomerism, it's like its pair will also be there, which is happens when the positions are around the meridian of the octahedron. When you have an octahedron structure, and at the meridian, if you place the positions of the donor atoms, then we get the meridional or mer isomer. Okay, so these are the facial and the meridional are the two another type of isomerism come under the geometrical isomerism, shown by the octahedral complex. So let's understand it with the help of figure 5.5. The figure 5.5 is this, which showing the facial and the meridional isomers of this complex, cobalt ammonia whole thrice, NO2 whole thrice. Okay, so cobalt is the central metal, okay, and it is arranging these all the 6 ligands in the octahedral manner. Now, when you are placing the 3 donor atoms, that is nitrogen, of the same ligand, let's say you are talking about the NO2 ligand, okay, from the NO2 ligand, the donor atom will be nitrogen, which are going to bond with the central metal with the coordinate covalent bond, right? So when these 3 donor atom of the same ligand NO2 is going to occupy the adjacent position at the corners of an octahedral face. So this red triangle is showing the that face at the corner of which the 3 ligand donor atom are present, okay, and this is forming the facial isomer of this complex. Similarly, if you are position the ligands at the or around the meridian of the octahedral, like in this structure, the cobalt is the central metal, the NO2 you are placing at the meridian of the octahedron, okay, the structure octahedral coordination entity occupying the octahedron. So octahedron meridian is this one, okay, and at the corners of this, so at the meridian of the octahedron you are placing the ligands, okay, the same ligand, then you will get the meridional isomer. Okay, so like imagine in the 3D structure, then you can understand more the facial isomer and the meridional isomer. Okay, so if basically you are placing the 3 donor atoms of same ligand at the corners of the octahedral face, so if you see, this is a this brownish color is a plane, okay, lying horizontally, okay, in the XY, let's say, okay, and this NH3 and the NO2 in the downwards is lying in the Z axis. Okay, so when you are combining this NO2 in the Z axis, in the ZY plane, in the ZX plane, and then you are combining this another NO2 and this another NO2, and they are forming the octahedral face, okay, imagine the 3D, and they are obtaining the corners of this octahedral face, then this structure which is formed by this placement is referred to as showing facial isomer. Okay, and when you are shifting the positions of these ligand of the same ligand at the meridian of the octahedron, okay, you can see in this in this plane which is lying in the like you can say horizontally, which is lying horizontally at the meridian of this octahedron, you are placing three ligands, same ligands, then you are getting the meridional isomer of this complex. Okay, so this is how the another type of geometrical isomerism is shown in the octahedral coordination entities or octahedral complexes in the 3D, if you can imagine. First is the facial isomer and the another is the meridional isomer, and we like cis and trans, we denoted them as FAC and MER. Okay, FAC and MER. Okay, now let's do an example here. First of all, 5.4. So the example is that why is geometrical isomerism is not possible in the tetrahedral complexes which is having two different types of unidentate ligands that are coordinated with the central metal ion. So we are asking that why there is in the geometrical isomerism is not possible in the tetrahedral geometry complexes which is having two different types of unidentate ligand. Okay, this is what we are needing in to show the geometrical isomerism, to place the two unidentate ligand adjacent to each other or either opposite to each other to show the geometrical isomerism, right? But still in the tetrahedral complexes, if it is having two different types of unidentate ligands in it, still it is not possible to show the geometrical isomerism in this. So why is it so? You have to tell the reason. Okay, you remember we have studied about it, so you have some time, try to analyze this question and then we will see the answer of this example. Okay, let's see. So for this given example, so let's first of all understand the tetrahedral complexes. Central metal atom are surrounded or is surrounded by four ligands that are positioned at the corners of a tetrahedron. Okay, so at the corners of the tetrahedron we have four ligands positioned and that is forming the tetrahedral complex. Okay, so four ligands are positions at the corners of the tetrahedron surrounded the central metal atom and that is forming the tetrahedral complex. Now the bond angles that is going to be formed between the ligands, that they are approximately 109.5 degree. Okay, so in the tetrahedral geometry, in the between of the tetrahedral geometry we have central metal atom, and that central metal atom is going to be surrounded by four different ligands bonded to the four different ligands which are positions at the corner of the tetrahedron in the tetrahedral geometry. Okay, the bond angle between the two ligands, like you can say ligand central metal ligand, so the bond angle form is approximately 109.5 degree. Now in this case we are considering the tetrahedral complexes of type Ma2B2. So we are considering the tetrahedral of the standard type Ma2B2 where we have different types of unidentate ligand present. So here A and B are two different unidentate ligands. Now let's understand about geometrical isomerism, because we are asking about geometrical isomerism not possible in tetrahedral complexes. Why? So for the geometrical isomerism to exist the ligands in a complex must be able to occupy the different spatial arrangements. That means we should be able to change the spatial arrangement of the ligands around the central metal for showing the geometrical isomerism. Okay, and also that are not superimposable on each other. And also, if you change the spatial arrangement of the ligands around the central metal and you get the new structure, those two structures should not be superimposable on each other. That you should also have to consider for the complex to show the geometrical isomerism. Identical relative positions in the tetrahedral geometry. Now, what happens that in a tetrahedral complex with the two types of ligands, let's say A and B, which we are considering as of type Ma2, B2, no matter how the ligands are arranged, the relative positions of the ligands remain identical. Okay, so if we talk about the 3D tetrahedral geometry, where in the corners of the tetrahedron you are placing the ligands around the central metal. So in the tetrahedral complex with having two different type of ligands A and B which are unidentate, no matter how you are going to place those two atoms, those two ligands around the central metal atom, the relative position among the each other, okay, so the relative position of the ligands among each other is going to remain identical. This is because, now why this is happening, because the tetrahedral shape does not allow for distinct arrangements that would lead to the different isomers. Because it is for the tetrahedral shape, tetrahedral shape is having a particular bond angle, a particular bond length, and particular geometry arrangement of the atoms. Okay, so tetrahedral shape is not allowing for distinct arrangements of the metals or of the atoms that would lead to different isomers. Okay, and if the complex structure will not change, they are not going to form the isomer. Since the angles and the distances remain the same, the bond angle and the bond distances remain the same, regardless of how the molecule is rotated. Therefore, geometrical isomerism is not possible in the tetrahedral complexes with two different unidentate ligand. Even though they are having two different unidentate ligand, the geometrical isomerism is not possible in the tetrahedral complexes. So this is the correct reason that why geometrical isomerism is not shown by the tetrahedral complexes having two different types of unidentate ligands coordinated to the central metal atom. So let's see the another type of optical isomerism, or let's shift to our next subsection 5.4.2, optical isomerism. Optical isomers are the mirror images that cannot be superimposed on one another. So optical isomers are, let's say, two structures which are mirror images first of all of each other, and they cannot be superimposed on one another. Superimpose means you can't take one image and place at the another image. Okay, that means they are non-superimposable. The molecules or ions that cannot be superimposed, they are called as chiral. Okay, the arrangement around the carbon is going to be different in those molecules. These are also called as enantiomers. So the two forms are called dextro. So enantiomers and optical isomers, they are same, and they form two different type of isomers like dextro and levio, in the dextro form and the levio form. As geometrical isomer, remember geometrical isomerism showing two types of structure, cis and trans. Here the optical isomerism you can see in the two forms dextro and the levio, represented by D and L. Depending upon the direction, they rotate the plane of polarized light in a polarimeter. So polarimeter is basically a device which we use to rotate the plane of polarized light to know the optical isomerism, or to know the direction of to know the structure of our complex. Okay, so the two forms are dextro and levio, and it is depending whether it is dextro or levio on the fact that how the polarimeter, the plane of polarized light is rotating its direction. D means light is rotating to the right, and L means light is rotating to the left. This ability to rotate the plane of polarized light in the polarimeter is its optical activity. Optical isomerism is common in the octahedral complexes involving diadentate ligands, which you will see in the figure 5.6, while the square planar complexes rarely exhibit it due to the presence of a plane of symmetry. So what we are saying, that the optical isomerism you commonly observe in the octahedral complexes, in which the central metal is arranged or central metal is present and bounding to 6 different ligands. Okay, and it can also involve the diadentate ligand. Okay, diadentate means 2 donor atoms present in the same ligand, like ethylene diamine, which we will going to see in the figure 5.6. While if you talk about the square planar complexes, in which the central metal is arranged in the square planar geometry with 4 different ligands around it, so it is rarely exhibited in the, like, optical isomerism is rarely shown by the square planar complexes due to the presence of the plane of symmetry in that. Okay, you can see in the figure 5.6, optical isomers is shown in the dextro and Levio form for this complex cobalt En whole thrice whole 3 positive. Cobalt is our central metal atom or central metal ion, and around it the 3 molecules of the En diadentate ligand is arranged. Okay, so it is involving the diadentate ligand. It can act as, it is octahedral complex. How? Because each En can bound to the cobalt with 2 different donor atoms present in the same ligand. Okay, so with 2 different donor atoms, the En can bind to the central metal. That's why it is going to be a octahedral complex, because the cobalt, which is a central metal ion, is present in this complex, and surrounding it 3 molecules or 3 ligands or 3 diadentate ligands of En is present. Every one or every each the En complex or the En ligand is going to bond with the central metal ion with 2 bond with via its 2 donor atoms present in it. So that's why 6 bond is forming in this whole complex with the between the central metal ion and the diadentate ligands. Okay, now when you form the mirror image by putting a mirror in between, mirror image of this dextro form, this is going to form something like that. Now these are non-superimposable. So basically if you took this image, this dextro image as it is, and put it here as it is without flipping or anything, it can't superimposed. Okay, so that's why they are non-superimposable. And this is dextro and this is Levio. Levio means it is rotating the plane of polarized light in the left direction, and dextro is rotating the plane of polarized light in the right direction. Okay, so these are the optical isomers in the dextro and Levio form of the complex cobalt En whole thrice whole 3 positive. Okay, now in a coordination entity of type platinum Cl2 En whole twice whole 2 positive, only the cis isomer shows optical activity. Okay, this you will see in the figure 5.7. So if you have a coordination entity of this type, where this is the complex ion, this will show only the cis isomer. Okay, for this coordination entity of this type, platinum Cl2 En whole twice whole 2 positive, only its cis isomer is going to show the optical activity. Let's see this in the figure 5.7. So it is showing the optical isomer of Devio and Levio form, dextro and Levio form of cis platinum Cl2 En whole twice whole 2 positive complex. Okay, so cis form of this complex. Cis form means, remember, this is X2LL2 type. This is MX2LL2 type, where LL is a diadentate ligand. Okay, and you can arrange this chlorine either in the adjacent form to get the cis, or opposite to each other to get the trans form. So the cis form of this cis isomer of this complex is going to show the optical activity. So we are only taking the complex where chlorine is present at the adjacent position of each other. So platinum at the center, chlorine is at the adjacent to each other. Similarly, the ethylene diamine is present at the adjacent to each other. And you can arrange it like this also and like this also, dextro and levio form respectively, by putting a mirror in between and getting the mirror image of one. Okay, so dextro and levio form, they are non-superimposable, and they are the cis isomer of platinum Cl2En whole twice whole 2 positive complex, which is showing the optical activity like this in the form of dextro and levio. Okay. Okay, let's solve an example 5.5. The example is, draw the structures of geometrical isomers of the complex iron NH3 whole twice Cn whole 4 whole negative. Okay, so this is the complex, this is the formula, and you have to draw the structure of this geometrical isomer. So try to solve this, then we will see the answer for this. Okay, let's see. So for this example, the octahedral complex of the type Ma2B4. So we have given this complex iron NH3 whole twice Cn whole 4. Okay, so this is of type Ma2B4, where A is ammonia and B is cyanide. Okay, these two different ligands are present in this complex. 2 plus 4 means 6, so this is an octahedral complex, and the octahedral complex of this type Ma2B4 exhibit two geometrical isomers, because we are talking about the geometrical isomers of this complex, and the two geometrical isomers shown by this complex is cis and the trans form. So the structure of these geometrical isomers are this: the iron arranging the two ammonia adjacent to each other, and other positions is occupied by cyanide ligand, so this is the cis form. And when the iron is arranging the two ammonia opposite to each other, and the other positions are occupied by the cyanide ligand, then you are getting the trans form of geometrical isomers of this complex FeNH2 NH3 whole twice Cn whole 4 whole negative. Okay, so these are the respective geometrical isomers for this complex in the cis and the trans. Let's solve the another example 5.6, which is that out of the following two coordination entities, which is chiral or optically active, that you have to tell. We have given two complexes here. First is cis chromium Cl2 oxalate whole twice whole 3 negative, and the B is trans chromium Cl2 oxalate whole twice whole 3 negative. So you have to select from these two coordination entity the one which is chiral or optically active. You have given some time, try to solve this, and then we will see the answer for this complex for this example. Okay, let's see. So let's see one by one. The first part is given as cis chromium Cl2 oxalate whole twice whole 3 negative. So its structure, so in the cis isomer, the two identical monodentate ligands of chlorine are going to be adjacent to each other, right? That is going to be the structure of cis isomer. The two biadentate oxalate ligands is occupying the remaining positions after the occupation of the adjacent position of the ligand chlorine. Symmetry elements. So let's visualize the cis form because we are considering the cis form. So imagine that the chromium is at the center of the octahedron because this is an octahedral complex where two ligands are unidentate and the two ligands are diadentate. Now two chlorine atoms are going to be on the adjacent corners of the octahedron. The two oxalate, the diadentate ligands, each going to span two coordination sites, the remaining sites. And this cis isomer does not possess a plane of symmetry or a center of inversion. Both type of symmetry is not going to be present in this cis isomer. So plane of symmetry will not be present. Plane of symmetry means, so plane of symmetry arises when along the plane or in the plane, if you are along one axis or along any axis, you are obtaining any symmetry or similar like ligands or side atoms are going to be present along that axis in a plane, then the complex is going to possess the plane of symmetry. So this cis isomer is not going to possess any kind of plane of symmetry or a center of inversion. It exists as a pair of non-superimposable mirror images or enantiomers. Okay, so it is existing as a non-superimposable mirror images, which is essentially to be as a optically active compound or a complex, right? So it will going to be present as an enantiomer. Let's check the chilarity. So because it lacks the plane of symmetry and a center of inversion, cis isomer is chiral. That means optically active. Okay, because this is not containing any kind of plane of symmetry and the center of inversion. So plane of symmetry, I explained. Center of inversion comes when around the center, like if you go from the center to the distance in any direction, you get a ligand. And in the similar opposite direction, if you go to the same distance and you find the same ligand, then there will be a presence of center of inversion. But here in this cis complex of this, or cis isomer of this complex, it didn't have plane of symmetry and the center of inversion both. That means it is chiral. This cis isomer is chiral. That means this is optically active. Let's see the trans isomer of chromium Cl2 oxalate whole twice 3 negative. If you talk about the structure of it, in this trans isomer, two identical chlorine ligands which are monodentate are going to be present at the opposite of each other or opposite to each other. And the two biadentate oxalate ligands occupy the equatorial plane, the remaining sides. Now the symmetry element, let's check. So if you visualize the chromium at the center of the complex, the two chlorine atoms are along one axis because they are placing at the opposite to each other, right? So two chlorine atoms are going to occupy the corners of the one axis, or along the one axis they are present, for example top and bottom. Now the two oxalate ligands lie in the plane perpendicular to this axis. Okay, so if you observe or if you imagine in the 3D, we have octahedron structure, octahedral complex in the trans form, where along axis you have placed two chlorine atoms and the remaining sites will be occupied by the diadentate oxalate ligand. So let's say at the top and the bottom, if you are putting the chlorine atoms along this axis, the two oxalate ligands lie in the plane perpendicular to this axis, right? Because the remaining bond will be present there. The 4 bond is going to be present in the plane, horizontal plane, and there is one axis coming out of the plane and one axis coming down below the plane, going below the plane, right? But along this axis, like in the top and the bottom positions, we have two chlorine atom already occupied. The remaining positions which is present in the plane, in the horizontal, is going to be occupied by two oxalate ligands which is perpendicular to the axis. Now this trans isomer possesses a plane of symmetry. Okay, now here the plane of symmetry is going to be present. How? Due to that horizontal plane is going to divide the two chlorine atoms equally, right? So the trans isomer possesses a plane of symmetry that passes through the chromium atom. Okay, that horizontal plane which is passing through the chromium atom and bisecting the both chlorine chlorine and oxalate chromium oxalate planes. Okay, so that's why there is a presence of plane of symmetry. And it is also possessing the center of inversion at the chromium atom, because if you move from the chromium to the chlorine at the top position of axis, similarly if you go in the same to the same distance in the bottom of this axis, you will find again chlorine. So this trans isomer is also possessing the center of inversion around the chromium atom, which is central metal ion. Now if you check the chilarity, so because it is possessing plane of symmetry and a center of inversion both, trans isomer is achiral, that is it is optically inactive. And it is also the superimposable form on its mirror image. Okay, it can be superimposable on its mirror image. So the two entities are represented as, the first is this one, the cis form, and the another is trans form. Okay, chromium is the central metal ion. Two chlorine when present adjacent to each other, it is forming cis, and when two chlorine are present opposite to each other, it is forming trans. This is optically inactive and this is optically active. No presence of plane of symmetry or center of inversion is present in the cis isomer, and plane of symmetry and center of inversion is shown by the trans isomer. So out of the two, the A, that is cis chromium Cl2 oxalate whole twice whole 3 negative, is going to be the chiral or optically active. Let's see the another isomerism, which is linkage isomerism 5.4.3. So this arises in the coordination compound which is containing ambidentate ligand. So in a coordination compound or in a coordination complex, if you are having the presence of ambidentate ligand, then that coordination compound is going to show the linkage type of isomerism. Okay, now what is ambidentate ligand? We have studied about it. So if a ligand can bind through, or in a ligand, if there are two donor atom are present which can bind through the central metal ion, then that ligand is going to be considered as ambidentate ligand. Okay, for example, SCN. In that SCN, through sulfur and through nitrogen, both through both the atoms, through both the donor atoms, the ligand can bound to the central metal ion. Okay, for example, a complex which is containing a thiocyanate ligand, as I said, NCS negative ligand, which may be bind through either nitrogen to give NCS type of complex, and also it can bind through sulfur to give SCN type of complex. Here MSCN means M is bonding with, metal is bonding with sulfur. Here MNCS means metal is bonding with the nitrogen atom of this thiocyanate ligand. So this is a ambidentate ligand. Jorgensen discovered such behavior in this complex, cobalt NH3 whole 5 NO2 Cl2. In this complex, if you can observe what is the ambidentate ligand present? NO2. Okay, NO2 is the ambidentate ligand, and because it is having, this complex is having an ambidentate ligand in it is going to show linkage isomerism. So he discovered that it is going to be observed, or it is going to be, this complex is going to obtain as in the red form when the nitrite ligand, this NO2 ligand, is bound through the oxygen to this cobalt. Okay, so when this ONO type of bond will form, that means oxygen will going to form the bond with the cobalt, the central metal ion, then this complex is going to obtain as red form. Similarly, it is going to obtain in the yellow form when the nitrite ligand is bound through the nitrogen. So it can, this is the ambidentate ligand, so it can bind through nitrogen and oxygen as well. So when it is binding through oxygen, this complex color is red, and when nitrite ligand is going to bound with the cobalt with nitrogen, the complex color is going to obtain as yellow. So this is the difference which Jorgensen discovered, or Jorgensen observed in this complex. Let's see the another type of isomerism, that is 5.4.4 subsection, coordination isomerism. This type of isomerism arises from the interchange of ligands between the cationic and the anionic coordination entities within the same complex. Okay, so within the same complex, if you are interchanging the ligands between the cationic and the anionic coordination entities, then the coordination isomerism is going to be arises. Let's see how. Let's understand by the example. So let's take an example of this complex cobalt NH3 whole 6, chromium CN whole 6. Okay, so cobalt, ammonia whole 6, chromium cyanide whole 6. Now in this, the ammonia ligands are bound to cobalt 3 positive, and cyanide ligands are bounding to the chromium 3 positive, right? So with the cobalt, ammonia is bonding, and with the chromium, cyanide is bonding. Now in its coordination isomer, how it can show coordination isomer? So we can written its isomer in this form, where chromium is bonding with the ammonia and cobalt is bonding with the cyanide. So here the ammonia ligand are bound to chromium 3 positive, and the cyanide ligands are bound to cobalt 3 positive. So this is the interchanging of ligands happens. Here what happens? These ligands of ammonia and the cyanide just interchange between the anionic and the cationic coordination entity, which is cobalt and the chromium here. Okay, so this NH3 is going to be like interchange the ligand cyanide and form the bond with the chromium, which cyanide was forming in the first complex. Okay, so if this is the initial complex, its coordination isomer will going to be in this form, where the interchange of ligands happen between the cationic or the anionic coordination entities within same complex. Within same complex it is happening, the interchange of ligands. Okay, so this is how the coordination isomerism can be shown by a complex. Okay, let's cover the summary. So whatever we have been studied in this lecture. So first we are cover the concept of isomers. So two or more compounds that have same chemical formula but different arrangement of atoms, they are considered as isomers. Geometrical isomerism we have seen, that which is commonly observed in the compounds having coordination number either 4 or 6. Now, geometrical isomers is not possible for a tetrahedral geometry. If the complex geometry is tetrahedral, it will not going to show the geometrical isomerism. And the facial isomerism we have seen, a type of geometrical isomerism when 3 donor atoms of same ligands is going to occupy the adjacent positions at corner of octahedron face. Then it will going to show facial isomerism. Similarly, the meridional isomer, when it is a type of geometrical isomerism when the positions of the ligands are around the meridian of the octahedron, then we will obtain the meridional isomer. Then we talked about the optical isomers, which are mirror images and they cannot be superimposed on one another. This is the property of them. And it is common in the octahedral complexes. The optical isomerism is common in the octahedral complexes involving diadentate ligand. And square planar complexes rarely exhibit this optical isomerism due to the presence of plane of symmetry in those. Linkage isomerism then we covered, which arises in a coordination compound containing ambidentate ligand. If a coordination compound is having ambidentate ligand, for example, if the complex is having NCS negative thiocyanate as a ligand, then that complex or that coordination compound is going to show linkage isomerism. Lastly, we will cover the coordination isomerism, which arises from the interchange of ligands between the cationic and anionic coordination entities within the same complex. So in a same complex, if the ligand is interchanging and forming the bond with the central metal and change their positions between the cationic and the anionic coordination entity, then the coordination isomerism is shown by those complex. Okay, so this is the summary of the content that we have been covered today. Okay, thank you so much. That's all for today's chemistry session. Thank you.